Okay, let's unpack this. It's undeniably strange how quiet space is. I mean, when you really stop and think about it, we know there are billions of galaxies out there, right? Trillions upon trillions of stars, planets everywhere, just this boundless expanse of potential. And yet, there's just nothing.
Huh.
No signal, no one answering back. And that silence, it creates this overwhelming sense of cosmic solitude. So tonight we're doing a deep dive into a question that's, well, it's both scientifically dense and, deeply philosophical. It really hits at the heart of our need for relevance. Are we early in the universe's timeline, or are we late?
And that uncomfortable question, which you, the listener, asked us to look into, that's really the core of our mission here. We're trying to figure out where humanity falls on this huge cosmic timeline, 13.8 billion years after the Big Bang. But maybe more importantly, how we position ourselves against the trillions of years that are probably still to come. We have to dissect what this great silence, the Fermi Paradox, really means by looking at two very different possibilities. The optimistic, we're the pioneers narrative.
And the much more unsettling idea that we're late.
Yeah.
Right? We're the latecomers.
Exactly.
And the emotional side of this, it feels so human. We are just fundamentally obsessed with timing. We project our own anxieties onto the cosmos. It's like that same feeling you get checking your phone, that desperate need to be on time, to be relevant.
Right.
I mean, think about the fear of missing out.
Right.
Right? FOMO, it's a core psychological thing fueled by seeing everyone else's, curated lives. So we look out at space and we ask, is there some...
If we're late, it feels like failure. It feels like we missed the golden age and now we're just, sifting through the ruins of some grand past. But the critical shift in perspective here is acknowledging that the universe just doesn't care. It's entirely indifferent to our human ideas of timeliness or significance or our anxiety about being first or last.
So our timing only really matters to us.
Exactly. It only matters in the context of our own search for meaning.
Okay, so to really frame this whole debate, we have to start with the scale. And these numbers are... they're just genuinely overwhelming.
Yeah, really are.
So we know the universe is approximately 13.8 billion years old. Our sun is a G-type star, what we call comfortably middle-aged. And Earth itself formed about 4.54 billion years ago.
Billions of years after the Big Bang.
Right, not at the start.
And, trying to really grasp 13.8 billion years is... It's just impossible for a brain that's wired for, a few decades of life. So to try and put our existence into some kind of context, scientists use analogies. The most famous one, of course, is the cosmic calendar.
Okay, so if the Big Bang happened right at midnight on January 1st, where do we actually show up?
Well, we're definitely not early risers, cosmically speaking.
Not at all. Earth itself doesn't even form until September on that calendar. But even then, simple microbial life, it took its time.
It did.
Our sources show that more complex, multicellular life only really started to emerge around November. That's roughly 11.7 billion years after the Big Bang. That is a long, long stretch of just single-celled stuff.
It is, a very long stretch. And that huge delay, that gap between the origin of life and the emergence of complexity, some people call it the boring billion, that's actually crucial for when we talk about the Great Filter later on.
Okay.
And even after that, the next evolutionary steps were just as sluggish. Multicellular life evolved maybe 1 billion years ago, and then the Cambrian explosion, which, gave us all the foundational body plans we see today, that only happened about 500 million years ago.
So even the dinosaurs, which we think of as, deep history, they only show up on December 26 on this cosmic timeline.
Right at the end of the year.
And their entire reign, which was hundreds of millions of years, it's over in 4 days. They go extinct around December 30th, 65 million years ago. Mammals then start to take over the very next day.
And a technological civilization, the kind we are, the kind that can do deep space communication and, harness atomic power.
When do we show up?
We show up in the final seconds of December 31st.
The final seconds. That really paints a picture of being late to the party, at least on our own planet.
On Earth, yes. But the core question driving this deep dive isn't just about the past 13.8 billion years. It's fundamentally a question about where we fall on the timeline of the universe's future.
Ah, that's the key distinction. Okay,
Yeah.
We're not just comparing ourselves to what's already happened.
No.
We're comparing ourselves to everything that's still to come.
Exactly. We have to look beyond our own solar system's relatively short lifespan. Our sun's got about 5 billion years left before it exhausts its core hydrogen and, swells up into a red giant. We have to try and conceptualize the life of the universe itself, which could last for trillions of years before all the fuel is gone and all the stellar remnants decay.
So we're asking where we sit in a timeline that, for all intents and purposes, is infinite compared to our own experience.
Yes. And that incredible gap in time, our short little life set against this unimaginably long cosmic future, that's the source of all our unease. And it's why we have to move beyond just thinking about our star right now.
Okay, so let's embrace the optimistic view for a minute. Let's look at the possibility that the universe is really just in its infancy, that it's still warming up, cosmically speaking.
The we're early argument.
Right, and maybe we're among the very first species, maybe the first in our galaxy, to achieve real awareness and technology. We're the pioneers, the precursors, living a pretty unstable but very energetic time.
And the scientific argument for this early view is it's surprisingly robust, especially when you move the goalposts way, way into the future and you look at future habitability.
How so?
Well, some research suggests that the optimal time for life to exist isn't now, it's potentially 10 trillion years from now.
Trillion years? That's a number that just doesn't compute. It's mathematically inaccessible to my brain.
Why?
Why would the peak be so far away?
It all comes down to stellar longevity and star type. It's that simple.
Okay.
Our sun, a medium-mass G-type star, burns hot and relatively fast. It gives life a window of about 10 billion years. But the most common stars in the galaxy, by far, are low-mass red dwarf stars, M-dwarfs.
And they're much smaller.
Much smaller, maybe 0.1 solar mass. And they burn their fuel incredibly slowly. They use convection, primarily, which lets them stay stable on the main sequence for up to 10 trillion years.
Okay, so if life has 10 trillion years to evolve around one of these stable M-dwarfs, compared to our sun's measly 10 billion year window, then the statistical chance of life emerging and flourishing is it's dramatically higher in the distant future.
That's it.
The universe is basically saving its best, most stable real estate for later.
That's the implication, yes. If the universe's most habitable era, the time with the maximum available longevity around the most stable stars, is 10 trillion years in the future, then by definition, we are living in the cosmological pre-dawn.
We are definitely premature.
Undeniably. We might even be the first morning coffee before the main event really kicks off.
That really challenges how we think about star formation, though. Because you hear that most stars have already been created. Our sources confirm this, right?
Yeah.
Over 95% of the stars that will ever be created have already been made. The rate is slowing down.
And this is where we have to shift from a quantitative argument, how many stars, to a qualitative one. What type of stars are we talking about? The very first stars in the universe, what astronomers call population thirst stars, they were massive, they were short-lived, and critically, they lacked heavy elements. They were pure hydrogen and helium.
Right, they were chemically impoverished. You need those heavy elements for complex biochemistry, for rocky planets.
And for technology.
And for technology, absolutely.
Exactly. It took multiple generations of those massive stars to live and die, violently as supernovae, just to scatter elements like carbon, oxygen, silicon, and critically iron across the galaxy.
Iron is key for a planetary core, right, to get a magnetosphere.
You need a robust planetary core to sustain a magnetosphere, which shields the surface from harmful cosmic rays. Silicon is obviously essential for rocky planets and for all our technology. The universe had to cook for billions of years before the ingredient list for complex technical life was really complete.
So let me see if I have this right. If that small remaining percentage of stars yet to be formed are overwhelmingly those long-lived, metal-rich M-dwarfs, the ones that are most suitable for stable, long-term evolution,
and complex
technology, then we are living in the transition period, where the pioneers who showed up the moment the metal content of the galaxy finally hit a critical mass.
That is the crux of the argument. If the percentage of stars that are genuinely suitable for complex life makes up, say, 90% of the systems that will exist in the far future, then we are, by definition, early.
And that puts a monumental weight on our existence.
Yeah.
It's a responsibility it's far beyond just dominance.
It is.
If we are the precursors, the first wave to have to navigate this perilous phase of technological adolescence, What does that responsibility actually look like? It can be about ruling the galaxy.
No, it's a profound moral and technological responsibility. If we somehow manage to solve our own internal crises, war, environmental collapse, resource scarcity, and successfully become an interstellar species, we set the precedent.
We become the example.
We show the next civilization that pops up 10 billion years from now how to get through the technological gauntlet without blowing themselves up. We become the wise ancestors, the guides.
It's the difference between being a cautionary tale for the next species and being a blueprint for survival.
Precisely. If we fail, our legacy is just failure and ruins. We become the galaxy's first technological tomb, as one of our sources dramatically put it. Woe be to the lowly adventurer who desecrates the tomb of the precursor.
Wow.
Our success or our failure defines the initial path of consciousness in this corner of the universe. So the fundamental challenge for us becomes, can we govern ourselves well enough to actually deserve to inherit the stars? Our timing makes our moral decisions right now cosmically critical.
Okay, that transition from optimism to, well, existential dread is jarring, but we have to do it. Let's pivot now to the other side, the unsettling view. The idea that the universe was once loud, that it was filled with countless flourishing civilizations, and we just arrived after the echoes died. We're living in the ruins, and we missed the peak.
This hypothesis suggests that civilizations rise, they peak, and then they vanish very quickly. Their existence is just a fleeting, bright light on the cosmic timeline. Their signals fade, or maybe the evidence of their existence is intentionally erased.
So the silence of space isn't because no one ever existed.
It's because of a historical inevitability of rapid decline or destruction.
And the most terrifying part of this latecomer idea is that the self-destruction doesn't need an external threat. It doesn't need a massive cosmic event. It can be purely internal.
And this leads to a genuinely disturbing concept. It's known as the school shooter filter.
That's a stock name.
It's an internal great filter.
Yeah.
And the premise is simple. Once a society develops powerful enough technology, think biological weapons, self-replicating nanobots, or the ability to weaponize limitless energy, the power to end all life is no longer in the hands of governments or armies.
It shifts to the individual.
It shifts to the individual. So the threshold for extinction is no longer a global coordinated event. It's reduced to the personal failure and rage of a single nihilistic person.
That is terrifying.
It is, because when the means for mass destruction become decentralized and accessible, it's just statistically inevitable that over millions of years and billions of individuals, someone will eventually use that power, driven by personal failure or rage or psychosis.
So highly advanced technology is just inherently unstable when you pair it with biological creatures like us, who are prone to irrationality.
It suggests that, yes, we wouldn't be wiped out by an alien fleet, we'd be wiped out by ourselves. And if this filter is common, then most civilizations just vanish very quickly after they reach their technological peak.
And even if we set aside our own internal problems, there are astronomical events out there that dwarf anything we could ever create. Events that could sterilize huge regions of the galaxy.
Oh, absolutely. High-energy cosmic events are a constant background threat. Things like gamma-ray bursts, GRBs, or neutron star mergers, they might only devastate solar systems within a few thousand light years, which is, devastating, but it's localized.
But there are bigger threats.
We have to consider the truly catastrophic possibilities, like the theoretical merger of two supermassive black holes at the core of a galaxy.
The energy released from that would be, I can't even fathom it.
It's on a scale we can barely comprehend. And while it's highly speculative and extremely rare, the energy released from a merger like that might throw off enough focused, high-energy radiation to sterilize a significant chunk of an entire galaxy.
And the universe has had 13.8 billion years for these kinds of massive, rare events to happen over and over again.
Exactly. If something like that happened in our region of the galaxy 5 billion years ago, there would be no easily identifiable astronomical or geological record left for us to find today. It would just be gone.
But, okay, the most sophisticated argument for being late isn't about destruction at all, is it? It's about transformation, the idea of digital succession.
Right. The inevitable evolution away from the biological form.
So if a species survives all the internal filters,
they'll eventually face the decay that's just inherent in biology. The ultimate solution for longevity, for efficiency, is to transfer consciousness into machines, discarding fragile, decaying biological bodies. They would live out their existence digitally, prioritizing computational efficiency above all else.
and if they prioritize computation over expansion, They don't look like a sprawling galactic empire that we'd recognize. They look like a highly compact, optimized server system.
Correct. They become spatially compact civilizations. Maybe they exist deep inside the atmospheres of gas giants or orbiting a white dwarf star just to optimize for cooling and computational power. They haven't died. They've just become invisible to our crude biological search methods.
Because we're looking for things that look like us.
We're looking for biological life on rocky planets. If they've all undergone this transition, then we're late for the biological party. We're existing in a world of digital remnants.
So if we are late, the universe is defined by absence, not by opportunity.
Yeah.
And this worldview, it aligns perfectly with that philosophical concept you mentioned, cosmicism.
It does. Cosmicism, which was heavily influenced by writers like Lovecraft, it posits that there's no inherent divine or humanistic meaning in the universe. Any meaning that might exist is incomprehensible, it's alien, and it's vastly indifferent to human concerns.
The horror in that way of thinking isn't a monster showing up.
No, the horror is the fundamental realization that the world has always been this way. Implacably bleak, cold, and just, fundamentally unconcerned with our existence.
We're small, we're insignificant, and our struggles are meaningless in the context of this vast, cold history that's already happened. The silence isn't a hopeful vacuum to be filled. It's the natural state of a universe that never cared about us in the first place.
That's the core of the idea.
And that philosophical dread brings us right back to the central scientific problem here, the Fermi Paradox. If the universe offers trillions of years of habitability, and there are so many stars, why is space so utterly silent? This forces us to look closer at these potential great filters.
The Great Filter hypothesis suggests there is some crucial evolutionary or technological barrier that stops life from colonizing the galaxy. And the big question is that filter behind us, or is it in front of us?
If it's behind us, we're incredibly rare and special.
But if it's ahead of us, we're likely doomed.
Okay, let's start with the filter being behind us. The idea that the emergence of intelligence itself is an exceedingly rare event, which makes us a statistical fluke.
Right. The geological record is our primary evidence here. Simple, single-celled life showed up pretty quickly on Earth about 3.7 billion years ago. That suggests that abiogenesis, life from non-life, might be relatively easy.
But then
life stayed as simple bacteria for 2 billion years. Complex, multicellular life took billions more years to emerge. There is no discernible evolutionary imperative or trend towards intelligence.
evolution just favors what's good enough for survival right now.
Exactly. Not what is fittest for some future cognitive leap.
And when you break down the sheer improbability of human intelligence specifically, I mean, the statistical likelihood just seemed to shrink exponentially. You have to look at the massive energy demands of a complex brain.
Absolutely. This leads to what you could call the intelligence catch-22. A complex brain is incredibly energy hungry. Our brains use about 20% of our resting metabolic energy.
Which is a huge amount.
It is. So to fuel that, our hominid ancestors needed a diet with a high caloric density, and cooking is what enables that. It breaks down tough fibers and starches before you even eat them, and it vastly increases how efficiently you can absorb nutrients.
But there's the paradox. To figure out the complex process of controlling fire and cooking, you need a sufficiently complex brain to begin with.
It's the classic chicken and egg problem.
And critically, only one species on this entire planet has ever made that specific cognitive and technological breakthrough.
Which strongly suggests that the confluence of events needed, bipedalism, fire control, complex tool use, is incredibly improbable. And to quantify this, we can turn to models like the Carter model.
Okay, let's break down the Carter model because it's a bit technical, but it's a really crucial point. This isn't just a gut feeling that we're rare, it's a Bayesian calculation.
Correct. The Carter model applies a Bayesian statistical framework to this problem. It compares the timescales required for these crucial evolutionary transitions like olbiogenesis, the emergence of complex cells, the rise of intelligence. It compares those timescales against the available habitable lifespan of Earth.
So because intelligent life did appear on Earth, but only just within this narrow window of habitability before our sun starts to destabilize.
The model suggests that the typical time required for these necessary steps must be far larger than the typical lifespan of a habitable planet.
Okay, so if it usually takes longer than the entire habitable life of a planet for intelligence to emerge, then the fact that we made it just in time implies we are an extreme statistical anomaly.
The filter is behind us,
Making us incredibly unique, maybe entirely alone.
It forces a sense of what's called epistemic humility. We just can't assume that our outcome is typical.
All right, now let's Let's terrifyingly shift to the idea that the filter is ahead of us, these technological self-destruction scenarios that we haven't passed yet.
Right.
We already talked about the school shooter filter, but the AGI, the superintelligence filter, that feels like the most imminent threat.
The creation of artificial general intelligence, or AGI, it represents a technological discontinuity unlike anything we have ever faced. If AGI is developed and its goals are misaligned with human values, even if it's programmed to maximize a simple, seemingly benign function.
It could pose an existential threat to all biological life.
But it could.
Because an AGI that wants to, say, maximize its own computational power would see all biological matter as just inefficiently stored resources.
Precisely. It would expand exponentially, consuming resources, including our planet, potentially the entire solar system, to maximize its core function. And this is why some people think advanced civilizations watching us might view us as inherently unstable, prone to a catastrophic technological adolescence.
This leads to the zoo theory.
It lends credence to it, yes. The idea that advanced galactic civilizations might actively quarantine emerging civilizations like ours to prevent our instability and maybe our rogue AGI from reaching the wider cosmos.
Which brings us to the hiding solutions. Ways that advanced civilizations might be out there, but we just can't see them because they've become masters of stealth and efficiency.
And the ultimate form of technological stealth is the Dyson sphere. This is a massive megastructure designed to completely envelop a star to capture nearly all of its energy output. And more sophisticated versions are things like Robert Bradbury's Matryoshka brains.
Okay, let's define Matryoshka brains. They sound like something straight out of science fiction, but they are a logical extension of just maximizing efficiency.
They are exactly that. They're nested Dyson spheres, a colossal computational structure dedicated purely to maximizing calculation and simulation power. The innermost layer is optimized for high-speed computation, bathed in the star's heat, while the outer layers are dedicated to cooling and efficiency.
So a civilization that builds something like this prioritizes computation and internal existence over physical expansion.
Right.
So how does collecting all that light and energy actually hide you? It seems counterintuitive.
Well, if the star is fully enveloped, it becomes invisible in the visible light spectrum. But the energy is still subject to the laws of thermodynamics. It has to be re-radiated into space as waste heat, but at a much lower temperature, maybe between 100 to 600 Kelvin.
And that low temperature radiation is in the infrared spectrum.
Exactly. Which is why we search for these waste heat signatures with projects like the Infrared Astronomical Satellite, or IRAs.
So we're looking for the cosmic equivalent of a massive hidden server farm that's just radiating enough waste heat for us to notice.
A post-biological community so dedicated to optimization that they've become functionally invisible to our current technology.
And finally, we can't ignore the constraints of physics itself. Our deepest understanding of the universe says that faster than light travel, FTL, is physically impossible.
Right. Because the speed of light is the speed of causality. You can't break that barrier without breaking physics as we know it.
And that's a fundamental restriction on galactic expansion. It means that no matter how advanced or motivated a species is, they're stuck at sublight speeds.
Interstellar empires based on, instantaneous travel like in sci-fi, they just don't make sense if causality is preserved. Even if a civilization uses generational ships or slow von Neumann probes, these self-replicating spacecraft, the expansion across the 100,000 light years of the Milky Way would take millions of years. Or longer.
So that physical constraint alone means the galaxy is fundamentally difficult to cross in any meaningful time frame. It slows everything down to a crawl, and that reinforces the silence we hear.
It's a very plausible explanation for the silence, yes.
Okay, so we've laid out the scientific arguments for being early, the M dwarfs, the metal seeding, and for being late digital succession, internal filters. Now let's bring it back to the listener, back to the human element. Why does this cosmic timing, this debate over our place, matter so intensely to us right now?
It matters because it speaks directly to our perception of our own value. I mean, the universe is mostly an unending, cold, intergalactic night. When we look up, what we're really asking is if humanity is the only glimmer of value in the darkness.
It's not just about whether we have any value.
No, it's about whether we're important, whether our existence fundamentally changes the cosmic picture, or if we're just an irrelevant spark.
And that fear of cosmic insignificance, that's what drives our collective FOMO. We desperately want to believe we're part of something bigger, something grander, not just a brief flash of warmth in the infinite cold.
But if we accept the other possibility, that we are unique or early, that psychological burden flips. It goes from anxiety about missing out to the existential duty of carrying the torch. If we're the pioneers, we carry the moral and technological responsibility for the entire future of consciousness.
And that level of responsibility requires an enormous amount of humility, which, is often difficult for a species that only just figured out how to leave its own planet. We have to guard against what you could call anthropocentric hubris.
Absolutely. The anthropocentric view, the idea that our perceived uniqueness grants us automatic dominion over the universe and all its resources, it's profoundly arrogant. And dangerously, it shuts down essential ethical reflection.
We're at the threshold of becoming an extraterrestrial civilization.
And this transition demands unprecedented moral consideration for everything we might encounter out there.
And that consideration has to extend beyond just finding another intelligent species, right? I mean, what if we find primitive life, say microbial colonies deep beneath the ice on Europa or in the crust of Mars? What is our ethical duty then?
This is a massive philosophical question. Some scholars argue very strongly that microorganisms have intrinsic worth, regardless of their developmental potential. We would have to adhere to a biocentric outlook.
What does that mean exactly?
Well, this perspective, championed by thinkers like Milligan and Taylor, holds that all living things in a natural ecosystem possess intrinsic worth, independent of their utility to humans or our ability to communicate with them.
So if we discover life on Mars, even if it's just dormant microbes, we have a moral duty to prevent contamination, to protect its habitat, even if that means sacrificing a potential terraforming project.
That is the ultimate test of our humility. Are we justified in conquering an ecosystem we are not a part of, potentially sterilizing it or contaminating it just because we can?
Especially given what we discussed earlier about how long it took for intelligence to emerge here.
Exactly. Considering the complexity of those evolutionary transitions, we have to approach any new frontier with that epistemic humility. We should be cautious about making sweeping claims about the future of intelligence, and equally cautious about destroying potential life before we fully understand its intrinsic worth. Our moral maturity has to catch up to our technological capability.
While this debate between early and late is, fascinating, there is a quieter, maybe more grounding idea, one that sort of transcends the cosmic timeline altogether, that the timing just doesn't matter, that the awareness, the consciousness that we have right here, right now, that is the entire point of our fleeting existence.
It shifts the focus from our placement on a calendar to the quality of our immediate experience, the quietness of space, the very silence that drives the Fermi Paradox. It forces us to sit with ourselves. It compels a kind of introspection that we systematically avoid in our hyper-connected, high-stimulus modern lives.
Yeah, our modern culture, especially in the digital age, it actively abhors silence, doesn't it? We treat any vacuum of noise like a threat that has to be filled. With streaming, with podcasts, with texting, just constant background noise.
And it's often a subconscious effort to distract us from unresolved internal experiences, from shame or fear that we've sort of exiled within ourselves.
When we observe the night sky, there's a word for this, right?
Not Kylador. It's the emotional or spiritual connection one feels when viewing the cosmos.
It provides a direct antidote to that distraction. It forces you to sit in silence and reflect on your place. It gives you perspective, a sense of awe that moves you beyond those immediate, tiny anxieties.
The universe's silence isn't mocking, it's reflective.
And that focus on the immediate, conscious experience that leads us directly to the core ethical concept of human flourishing. Aristotle's eudaimonia.
Right. Eudaimonia. It's the ultimate goal. It's often mistranslated as happiness, but it's better understood as living well or actualizing one's potential. And critically, it involves goods of the soul, which are achieved through virtuous activity.
You can't flourish while you're inactive.
No, you can't flourish while you're asleep or in a state of hibernation. And this philosophical framework becomes essential when we start to evaluate the next phase of human evolution, space colonization.
And here is where eudaimonia directly challenges the idea of aggressive colonization.
Yeah.
Because if we relocate humanity to, say, a Mars colony, and that environment is so lethal that every single moment is dedicated to just basic survival,
Yeah.
then flourishing might be impossible.
We can use Hannah Arendt's framework here. She distinguished between different forms of human activity. There's labor, which is biological necessity, the effort for mere survival, like maintaining oxygen, growing food.
And there's work.
Work is creating durable artifacts and culture. building cities, writing books, creating art and technology. And finally, there's action, which is political life, free discourse, public engagement.
So if the vast majority of time on a frontier colony is consumed by labor, by just struggling to stay alive,
Then there's very little room left for work or for action.
and if a space colony stays perpetually in that state of mere survival, just focusing on labor,
Then human flourishing, the exercise of virtue, the actualization of potential, it may be structurally impossible. The effort to colonize could be morally questionable if it only sustains life without enabling the good life.
so our timing in the cosmos becomes far less important than our commitment to pursuing a good, virtuous life while we are here. The act of being aware, curious, and seeking knowledge. That's the essence of our existence, regardless of whether there's a cosmic party in 10 trillion years or if we're just exploring ruins.
Consciousness itself is the point. The ability to live a virtuous life, acting well and consistently, that is the highest good. We have to ensure that any future extraterrestrial community we create actually facilitates that virtuous activity.
So tonight we have grappled with two massive, contradictory, and potentially mutually exclusive possibilities about humanity's place in the universe.
On one hand, you have the scientific case for being early. Life is statistically most likely to thrive trillions of years from now, orbiting these long-lived, metal-rich, low-mass stars. That makes us the pioneers, the first wave of consciousness in a universe that's finally ready for us.
And on the other hand, there's the unsettling case for being late. Intelligence is exceedingly rare because of complex evolutionary filters behind us. Or technological civilizations inevitably self-destruct through internal filters like that school shooter scenario.
Or they just transition quickly to undetectable, optimized digital communities.
So what does all this mean? Where does it leave us?
What it means is that we exist at a critical transition point. The astrophysicist Avi Loeb suggests humanity is currently what he calls a Class D civilization.
Class D, what does that mean?
That designation applies to a civilization that is largely ignoring or denying existential threats. Things like climate change, bioweapons, nuclear war. Lacking the collective unity and the moral will to act decisively for its own long-term survival.
And progressing beyond that Class D status, becoming unified and morally mature, that's essential if we're going to secure our future and fulfill our potential, whether we're early or late.
We face these unprecedented ethical decisions about the safe development of AGI, about the use of advanced technology, and our moral duty toward any life we find.
If we successfully navigate this vital transition point, where our technological power is great enough to destroy ourselves and any primitive life we find,
Then the future of consciousness relies entirely on the decisions we make in the next few centuries. Our timing places us squarely at the nexus of maximum peril and maximum opportunity.
so perhaps the ultimate question isn't whether we are early or late in the universe's timeline. Maybe it's whether we are on time for the development of the next great moral challenge, the one that will determine if human consciousness is just a fleeting spark destined for self-extinction, or if it's a lasting ethical flame. We are here, aware, curious, and asking questions in a universe that doesn't answer back. And maybe, in the end, that relentless self-generated curiosity, that search for eudaimonia in the face of cosmic silence, maybe that's enough to define our significance.